Hello, students, and a very warm welcome. Today, we are going to tackle a very, very important topic from your Unit 3 Current Electricity. We're talking about cells, EMF, and internal resistance. Now, I know this can seem a little confusing, but trust me, we're going to break it down so simply, it will be crystal clear and absolutely perfect for your exams. So, let's get started. Okay, so here is our roadmap for today. We'll start by understanding the basic job of a cell. Then, we'll dive into what EMF and internal resistance actually are. We will also see the difference between EMF and what we call terminal voltage, clear up some very common mistakes students make, and finally, we'll wrap it all up in a neat summary for your notes. Shello, let's begin.
To really get this topic, let's start with a simple question that you must have faced in your daily life.
Just think about it, Beta. You get a brand new cell for your TV remote. It says 1.5 volts right there on the package. But if you were to actually measure the voltage while the remote is working, you'd find it's just a little bit less. This is a super common thing to see, and I promise you, by the end of this session, you'll know exactly why this happens.
So to answer that remote problem, we first need to understand the cell's basic purpose. What is its main job? Well, think of a cell like a pump for electric charge. Its only role is to provide that continuous push, that steady flow of energy to keep the current moving through any circuit you connect it to. Right, so let's now talk about the total, the maximum energy that a cell promises it can give. And this brings us to a term that is extremely important for your exams.
If you look inside a simple cell, what do you find? You've got two terminals, a positive one and a negative one, and they're both sitting in this chemical liquid called an electrolyte. It's the chemical reaction happening inside this electrolyte that does the work of separating the charges, creating an energy difference, what we call a potential difference, between the two terminals. And here is the main point. This maximum possible potential difference that a cell can create when it's just sitting there, not connected to anything, when it's in what we call an open circuit, that maximum value is its electromotive force, or EMF. We use the Greek letter epsilon for it. Just think of it as the ideal voltage, the cell's full potential, its maximum promise. A very simple way to remember this, and this is a great analogy, is to think of the EMF as the sticker price of the battery. You know, like the MRP printed on a product? That 1.5 volts written on the cell's cover is its EMF. It represents the total energy it can supply for every unit of charge before any of the real-world problems kick in.
Okay, so if EMF is the sticker price, why don't we ever get that full value when we actually use the cell? Well, it's because of a hidden problem, a little energy thief that's hiding right inside the cell itself.
You see, for the current to flow, the charge has to complete a full circle. That means it has to flow inside the cell too, through that chemical electrolyte. And that electrolyte, well, it's not a perfect superhighway for charges. It has its own little bit of traffic. It offers some opposition to the current flowing through it. And this internal opposition, this resistance to the current inside the cell, is what we call internal resistance. We use a small r to denote it. The best way to picture this is to imagine a tiny little resistor, we call it small r, sitting right inside our ideal cell. So every single time a current flows, some of the cell's precious energy is wasted. It's lost as heat, just trying to overcome this internal hurdle. It's like a small tax that the cell has to pay on its own energy. So, this brings us to the final piece of our puzzle, understanding the difference between what the cell promises, its EMF, and what it actually delivers to the outside world. Let's just walk through this logically. Situation 1, the circuit is open. No current is flowing. If you measure the voltage now, you'll get the full EMF. Perfect, but the moment you connect a bulb or a remote and a current I starts to flow, there's an energy loss inside the cell. How much? It's equal to I times R, so the actual voltage that's available outside, which we call the terminal voltage V, is the original EMF minus this internal loss. And this gives us the most important formula for this topic, V equals epsilon minus IR. This table is fantastic for your notes, so pay close attention. On one side, you have EMF. That's the source, the cause, the total energy the cell has. On the other side is terminal voltage. That's the effect, the energy it actually delivers. EMF is a constant value for a given cell, but the terminal voltage, that changes. It drops as you draw more current. And the final point to remember, EMF is measured in an open circuit, whereas terminal voltage is measured in a closed working circuit. So let's finally go back to our first question about the remote control. We can now use our new formula,
V equals epsilon minus IR, with some really simple numbers to see exactly what is happening.
And there it is. Let's say our new cell has an EMF, the sticker price, of 1.5 volts. And let's say its internal resistance is a tiny 0.2 ohms. Now, if the remote needs a current of 0.5 amps to work, what's the internal voltage drop? Well, it's I times R, so 0.5 times 0.2, which is 0.1 volts. So the terminal voltage delivered is 1.5 minus that 0.1, and that gives us 1.4 volts. And that's why the 1.5V battery only delivers 1.4 volts to the remote. Simple, isn't it?
Now, let's talk about a very common mistake that I see students making in exams all the time. Getting this right can save you some very precious marks. But Joel, please remember this. The name electromotive force is so misleading. It's a historical name that has stuck around from a time when people didn't fully understand the concept. For your exams, you must be absolutely clear. EMF is not a force, it is a potential difference, it is a voltage, and its unit is volts, not newtons.
Okay, here is a tricky question, a silent killer that can pop up in competitive exams or even in your Viva. We just learned that V equals epsilon minus IR, which seems to mean that V is always less than epsilon. But is that always true? Can the terminal voltage ever be greater than the battery's EMF?
And the answer is yes, it can. There's one very special situation, when you are charging a rechargeable battery, like in your mobile phone. Think about it. The charger is forcing current into the cell, in the opposite direction of its normal flow. So in this case, the charger's voltage V has to fight against and overcome both the battery's own EMF and its internal resistance. So the equation actually flips. It becomes V equals epsilon plus IR. And that's why, during charging, V is actually greater than epsilon.
Right then, let's quickly go over everything we've learned and summarize it into a few simple, exam-ready points.
But before we just list the points, it's really important to see how this topic connects to the bigger picture. The very next major topic in this chapter is Kirchhoff's rules. And when you apply Kirchhoff's loop rule, what are you doing? You are simply adding up all the EMFs and subtracting all the voltage drops around a circuit. That includes the internal drop, I(r) that we just discussed. So you see, what we learned today is a fundamental building block for solving more complex circuits later.
Okay, let's lock in these crucial points. 1. EMF, or epsilon, is the maximum voltage a source has, measured in an open circuit. 2. Internal resistance, small r, is that hidden resistance inside the source itself. 3. Terminal voltage, V, is the actual voltage you get when current is flowing, and its formula is V equals epsilon minus IR. And finally, from this, we know that the total current a cell can give to a circuit is the total EMF divided by the total resistance, which is the external R plus the internal R.
And that leaves us with one final thought to ponder. Since every single real-world battery has this internal flaw, this R, what do you think is the absolute maximum current you could ever possibly draw from it? I mean, even if you just connected its two terminals with a perfect wire, a short circuit, this internal resistance actually puts a physical safety limit on what the cell can do. Think about that.